In this video, I'll show you how to solve the ALEKS problem called recognizing and naming close-packed crystal lattices. So this problem is going to start off actually looking just like this. It's going to have one little visual of a crystal lattice. I've got some additional screenshots on here to help you see what it's going to look like. I've got a slider bar that lets you zoom into this crystal lattice, and we've got two questions to answer. First of all, whether or not it's a close-packed crystal lattice, and if it is, what is the type of crystal lattice? So what I want you to do with your slider bar is just immediately drag it all the way to the right. There's not a lot of information that we can get from the top layer of the crystal lattice, and also not a lot of information that we can get from like the middle layers of the crystal lattice. We just want to go all the way to the very end. I'll stick that right on top. You can see that I didn't drag mine all the way to the very end, and that's okay. You don't have to go all the way to the very end. What we're going to do is analyze what the crystal lattice looks like at the very end, at this point right here. Now, if it is a close-packed crystal lattice, there are going to be two different options for the type of crystal lattice that you're looking at. One of the types is the hexagonal close-packed crystal lattice, and you can use that abbreviation HCP. ALEKS does accept that. The other type is the cubic close-packed. And so I think what is the easiest way to solve this problem is to look for the hexagonal close-packed structure or the cubic close-packed structure. If you've got one of those, then that's the answer. And if you can't find hexagonal close-packed or cubic close-packed, then that means that no, you don't have that particular type of crystal lattice. So let me draw pictures of what you would expect to see if you have hexagonal or cubic close-packing. I'm going to draw the cubic close packing first because I think it's easiest to draw. So for the cubic close packed, you're going to see a few layers of spheres, and these layers of spheres are going to be offset from each other. You see how I'm kind of drawing them offset. I don't really even know a better word to describe it, but let me show you exactly what I mean. So this would not be a close packing situation, but when they're kind of offset and they're able to fit in those little gaps of the atoms around them, then that would be considered a close packing situation. And in the cubic close packing situation, you're going to have these spheres of one color that are all just kind of packed side by side with respect to each other. And then you're going to see smaller spheres that are fitting into these little gaps or holes that are left behind in the close packing process. So you're going to see something like red atoms squeezed in those little gaps right there, and then maybe some green atoms squeezed in the little gaps right there, and some green atoms right there. And some red atoms right there. And that would be what a cubic close packing lattice would look like. And as we're looking at my crystal lattice over here, we can see that this crystal lattice is not matching this cubic close packing pattern. And the reason that I know that, even though I haven't dragged my slider all the way to the end, is notice how my red atoms are sitting right on top of my blue atoms. And in the cubic close packing structure, the red atoms, if I had that, the red atoms would actually be located in these gaps right here. So the red atoms wouldn't be sitting on top of the blue atoms, and in fact there wouldn't be anything on top of the blue atoms at all. So I don't have cubic close packing. I'm just going to kind of slide this guy out of the way, and I am going to attempt to draw what hexagonal close packing looks like. So it is going to start off the same way. The blue atoms, you're going to see the blue atoms that are offset from each other, so they're sitting in these gaps right here. And again, this is just close packing, meaning that the atoms are fitting as closely together as they possibly can in this structure. And then you're going to see one type of atom. I'm going to go with green. You're going to see one type of atom that is fitting into the gaps in these spaces, but it's not fitting in all of the gaps. You can see in my little drawing here, some of these gaps or holes are going to be left empty. So some of them are going to be left empty. And then your third type of atom I'm going to draw as the red atom. That third type of atom is going to be sitting on top of another layer. So kind of matching my structure here, my third type of atom, which is the red atoms, they're sitting right on top of the blue atoms. This is hexagonal close packing. So since I do have this pattern right here, I am going to say, yes, I do have close packed crystal lattice, and the type is hexagonal close packing. With yours, as you're scrolling across, you get yourself all the way to the end. If you don't see this pattern, and you don't see this pattern, then your answer here is no, you do not have a close packed crystal lattice, and then you're not going to answer this second question at all. Now, I do want you to be careful. You're not necessarily going to see the exact same colors as me, but you should be able to see this pattern, this repeating pattern, either this pattern right here or this pattern right here. And if you see one of those two, then you'll know that it is either hexagonal or cubic close packed.